in this lesson, we're going to write down the formula for the pressure difference between 2 points in a fluid. Now that fluid could be a liquid or a gas. And let's look at this container here, supposing it's filled with a fluid, okay, and we want to measure the pressure difference between 2 points in that fluid. Say, for example, between this point and this point. Okay, so they're separated by a height h, and the height is going to be measured in meters. Now the fluid will have a density, rho, and the density is going to be measured in kilograms per meter cubed. So what I'm going to do first of all is I'm going to state the formula for the pressure difference between these 2 points. And we can say that the pressure is equal to the density of the liquid multiplied by the height difference between the 2 points multiplied by g, which is the acceleration due to gravity. Okay, so the reason why this density must be, and this is very important, in kilograms per meter cubed, is because in this formula the acceleration due to gravity is in meters per second squared, and we need to maintain the units coherent. You cannot have g in meters per second squared and have density measured in grams per centimeter cubed. It doesn't work. If we've got meters here, we must have meters there. So it's very important in any problem concerning density differences in a fluid, you always make sure that you've got the density in kilograms per meter cubed. And likewise, because we've got meters here and meters here, then the height must also be measured in meters. Keep the units coherent. Okay, so there's the formula, and it's a fairly simple formula. Again, if you're a little bit ropey about manipulating these formulas, remember the calculation triangle. And in this case, we've got something is equal to something multiplied by something multiplied by something. This is one of the very few cases in the GCSE syllabus where you've got a formula where there are 4 variables rather than 3. But the principle is exactly the same. We're going to put the pressure up here, and then the rho times the height times g underneath. Now we'll come back to using this expression later on. I'll give you a sample problem. But first of all, what I'm going to do is I'm going to prove this formula for you. Now, I would like to say this. You do not need to prove this for the GCSE syllabus. You simply need to know the formula. But I'm going to prove it anyway because it's a good thing to do. And it's also quite an easy thing to do. So what we're going to say then is, just to make life a little less complicated, what I'm going to do is I'm going to ask, what is the pressure at the bottom of this container with this fluid? What is the pressure produced here? Okay, so we're asking, what is the pressure at this point, at the bottom of the container? And we're going to say that h is the height difference between the bottom of the liquid to the top of the liquid. Okay, like that. And we're going to say that the container has a cross-sectional area equal to A. Okay. Now then, we remember that the pressure produced at this surface, well, we learned that the other day, P is equal to the force applied by the body, the liquid, divided by the area of contact with the surface, F divided by A. That's the simple standard formula for pressure. So we've got to ask ourselves, first of all, what is this force here acting downwards? Well, the force is equal to the weight, which is equal to the mass of the fluid multiplied by G. So you can say the pressure is equal to mass times G. I put a little dot there, that means multiplied by, and then divided by A. Okay, you've got that. Next we ask ourselves, well, what is the mass of the liquid? Well, we remember that the density rho of a substance is equal to the mass divided by the volume. So the mass of the substance is equal to the density multiplied by the volume. So we can now substitute this into our equation here. So that gives us rho multiplied by the volume multiplied by G divided by A. So just to finish off, all we've got to do now is determine what is the volume of this container. That's easy to do because we can see it's a cylinder, and the volume of a cylinder is equal to the area of its cross-section multiplied by the height. So let's just make a note of that. We can say that the volume is equal to the area multiplied by the height. Let's substitute that into our formula, and that gives us rho multiplied by A multiplied by height multiplied by G, and then divided by the area. So let's just make a note. The A's cancel. Let's put a cross through those. So we can say that the pressure difference in a fluid between any 2 points, what we've stated here is between the top and the bottom of the fluid, but it's also true for any 2 points in that fluid. The pressure difference is equal to rho, the density of the fluid, multiplied by h, the height difference between those 2 points, multiplied by g, the acceleration due to gravity. I'll put a little box around that. This formula, it is important that you remember this formula for the pressure difference in the fluid, but you do not need to prove this. You don't need to do this stuff. This is just there for your interest, and it's really only appropriate for A level, but you do need to remember this. And you do need to remember, very important, that the density of the fluid must be given in kilograms per meter cubed. Now there's one important thing I'd like to point out about this formula for the pressure difference between 2 points in a fluid, and it is this, that there is no information whatsoever contained within this formula about the shape of the container. So what we mean by that is, if we want to find out the pressure difference, for example, in this very irregular shaped container between, say, that point and, say, this point, when we look at this formula, we'll see that the only variable really in the formula is the difference in height, because the density of the fluid, rho, is a constant, and the acceleration due to gravity, g, is also a constant. And so the only variable is the height difference between those 2 points. That's the only thing we need to measure. So providing we know the height difference there, we can calculate the pressure. It doesn't matter what shape the container is. This leads us to an important experiment by Galileo, who was intrigued by this formula and decided to put it to the test. And what he did was he took a beer barrel, which are pretty sturdy things, and he fixed a tube, firmly fixed a tube here with a good seal to the beer barrel, and started to fill the whole lot up with water. First the beer barrel, and then as the beer barrel was full, the water started to rise out the tube. Now the tube now and the beer barrel are one single container, a bit like this funny shape here. Okay, really, they're just one single container, and then what basically happens is that the pressure difference between, say, that point there and the level of the water here only depends on the difference in height. That's what this formula really states. It's the density of the water and the acceleration due to gravity are constant. The pressure only depends on the height difference between these 2 points. So if you've got a tube long enough, then you can produce an absolutely enormous pressure in this barrel, which is just what he did, and the barrel eventually exploded, which must have been quite fun to watch. Anyway, in the next lesson what we're going to do is just have a look at using this formula, practicing it so that we can get it into our heads, again, it's absolutely no use just reading these things and not going away and practicing it. It's about as useful as, trying to learn tennis by reading a book. You've got to practice. You've got to practice with problems using these formulas. So we'll have a go at doing that in the next lesson. And then after that, we'll look at how to apply this formula to calculate the atmospheric pressure at the Earth's surface. Okay?